Hello everybody, I'd like today to talk about power calculation, and I would like to give some guidance about how we can calculate accurately without the problems we incur by using systems which are wire based, which are plasma or gas based in gas form, because they're all influenced by resonant frequencies on its own. So you get readings which are inaccurate, and because of that we need to have a so-called reference load which is unbiased. That means it will, under any influence, show always the same value. Only under that condition you can make a proper assumption or can give a proper result of your power findings, and that will hold up to the standard in the industry, and that will be also accepted in that form. It is not about to tell you whatever you do is wrong. That is not the purpose here. The purpose is to help everybody to find a way to make sense out of the readings you get and to reference these readings, here in my example with the reference load, if you can replicate that. And when your calculations are done via wire systems, maybe in a plasma or in a gas system, I can guarantee you will not get the same readings, because this is important for the reliability of what is said in the forum, and going forward to be accepted around the world with systems we are providing. We need to provide standard measurements to convince the scientific community that what we are doing is of great value and it has importance for the society. Power is part of our life here on this planet, where the main energy provider is our sun, which is responsible for all the powers we have on this planet. Might it be through heat, wind power, the moon, gravity power, on the water, the tides. All these energy systems are systems which are outside of the equilibrium, where a flow of motion of energy is moving from one side to the other, where the potential is changing. This is what we call power. We are focusing here on electrical power, and that means we have to talk about Ohm's law or Ohm resistance in subject, and I will go on to it in a second. Ohm's law and all his formulations about calculating around Ohm's law are the main calculations for our power calculation. So you can see here as a power function, P is the product of voltage times the current, and if you want to solve for the current, we have to divide the voltage squared by the resistance. So that's how we can derive in very simple fashion power. However, the way we are working in, it's not as simple, because we are talking about alternating current. So this is a simple example for direct current. For alternating current we have different things to calculate, and it becomes much more complex, because systems in an alternate current environment behave completely different, and that is one of the reasons we have all these problems in calculating power accurately. I have here the spec sheet of the system. As you can see, here's the details. You can see the tolerances, and you can see all the details for this resistor. It comes in variations, and of course the higher the resistance get, the more complex it becomes and the more expensive they are. So as I mentioned, between 30 and 50 pound, $50, but they can go up to a couple of hundred pounds and dollar for one resistor. Bear in mind, it's a reference load, so it has a specific functionality. So here in this example, this resistor does two things. First of all, it provides resistance. Second of all, it provides temperature from the ambient or temperature via the increased heat of this resistor as a load, and because of that we can calculate the deprivation from the norm. Such resistors are used for calibration of DMMs or other resisting calculating systems, and I will show you some examples for them. Can also be used for calibrating temperature measure systems which require Kelvin probes. We'll quickly scroll through some examples where you can see abbreviation. So this one is a 2.5% DMM. As you can see, it falls off the norm of 0.17 ohm. So it is within the tolerance. I go through a couple of different DMMs and I show you then also a precise measurement. So let's have a look at the next one. So this DMM, the M probe, is also in the same range of 2 to 4%. So you can see 10.3 ohm it indicates. Let's move on to another one. So this one is also toggling around the same subject, 10.1, 10.2. It's also in the same range. This is a little bit cheaper, so the tolerance is a bit higher on this one. However, it shows it more accurately, which would indicate that we have to calibrate the other ones. Now let's look how a precise instrument does measure. You see under my LCR bridge, you see a complete different frequency, and 1 kilohertz frequency. You see a complete different precision, 10.008 for example. If I go up in the frequencies, that's what 1 kilohertz. Let's have a look at 10 kilohertz. 10.007, and at 100 kilohertz 10.005. So that's the kind of precision you would expect from very expensive tools. This one was quite reasonable. However, good LCR tester can be many thousands of pounds as well. Well, if you're not really in the profession and you don't need to prove it to as an industrial standard, you probably don't need to spend so much money. However, if you have to provide proof to a scientific society, you have to use such kind of tool if you want to make some changes in society by providing accurate information. That's the way to go forward. For the systems we are talking about of alternating current, we have to deal with the subject RMS, which is a root mean square definition. As you can see here, the formulas for each waveform is different and very complex. So if we talk about, we have to talk about two values. One value is the value for voltage, for the potential, as the second value is a value for the current. Because remember, power is a product of voltage times current. So because of the difference or lacking or leading of current to voltage, there is at every different position of one waveform a different value available on a second waveform, and because of them they are not identical one-to-one or in sync, we have to derive different values of it, and that has a huge impact for power calculation.